So before we get into the area of polygons themselves, we need to go over the interior and exterior angles of polygons. So again, we're doing more properties of polygons. So an exterior angle is the angle that is on the outside of a polygon, continuing on a straight line to one of the sides. So if you extend one of the sides out, then the exterior angle is going to come from the other side all the way through to where that side straightens out. So in essence, the exterior angle is just the linear pair to the interior angle, because they're always going to add up to be 180. Here we have two examples, both of them showing that they are 180, so that they are a linear pair. Because remember, a linear pair is two angles that are next to each other that form a straight line. So any two angles. So if we have a straight line and any angle, those two are always a linear pair, no matter which way we deal with the angle. So those are going to be a linear pair because they add up to be 180 and they are right next to each other. So important thing to remember is that the exterior angle is just the linear pair to the interior angle. That means that they are going to add up to be 180, and this can be useful to prove different things about triangles. Did I just say triangles? So the exterior angles of a polygon add up to 360. So this is going to be true to no matter which polygon we have. So if we have a regular triangle, that means all of the insides are 60. So they're going to be sticking out. So the exterior angle would be 180 minus 60, which would be 120. So again, 120 and 120. So that means we'd have 120 plus 120 plus 120, or that would be equal to 3 times 120, which again is just 360. So if we go through all of the polygons, different polygons, whether it's a heptagon, a hexagon, a nonagon, a dodecagon, whatever we have, the exterior angles are always going to be 360 degrees when you add them all up, which could be useful because that means to find whatever for a regular polygon, the exterior angle, all we have to do is take 360 and divide it by the number of angles or sides we have. So to solve for the exterior angles, we just have to divide it by 360 by the number of sides we have. Remember, n is the number of sides, meaning for any gon we have it set as n gon. Number of side times the gon. So remember, a pentagon could be written as a 5 gon. A hexagon could be written as a 6 gon. So n just means the number of sides. Alright. So we can use the exterior angles to find the individual interior angles of regular polygons. Again, remember, regular meaning all equal sides and all equal angles. So a regular polygon would be evenly distributed of the angles. So all we have to do is divide the sum by however many we have. So one way we can use the exterior angle is that we know that the interior angle is 180 minus whatever that exterior angle is. Remember, for a regular polygon, the exterior angle is just 360 divided by n. So we can just substitute that in. That the exterior angle is 360 divided by n. So that gives us that the exterior angle is 180 minus 360 divided by n. Well, when we have that, we are dealing with a fraction. So that means we have to get this common denominator on a fraction in order to solve for it. So for them, the common denominator in this case, if we take out that n, It's 360 over n, 180 over 1. So to get a common denominator, we'd have to get n underneath the 180. Well, when we do that, we'd have to keep the same value while changing how it looks. So to do that, we have to multiply by a total of 1. So the value has to be 1, and so to get a value of 1, it has to be something over itself. So in this case, since we're looking for n on the bottom, it has to be n over n, so we can change how it looks without changing its value. So again, you can see right here, that's exactly what they've done. They've divided it by n. You can also see that they have taken out the 360 and factored it out to a 2 and a 180, because the 360 is just 2 times 180. So that would be 2 times 180 over n minus that n 180 over n. So when you do that, you say, hey, I can pull out a 180 on both sides. So when I do that, I have n minus 2 times 180. And again, all over n. So whenever we do that, we have our equation for the interior angles of regular polygons. That being 180 minus the difference of n and 2 divided by n. 180 times the difference, right? So that gives us that the sum is just 180 times n minus 2, and that each of the individual angles is 180 times n minus 2 divided by n. So these are the two main equations that you should keep in mind when you're dealing with the angles of a polygon. As you can see over here, we have some basic names and sides of polygons. It goes up to 40. So we have the triangle, interior angles of 60. So if we put the number sides n in here, we have n minus 1, which is 180. So we do know that the sum of a triangle's angle is 180. So that means 180 divided by 3 is, of course, 60. So you can see that right here. You can also see that it includes the other names of quadrilateral and triangle, being a trigon and a tetragon. Tri meaning 3 and tetra meaning 4. Alright, so all of these, the prefix is just meaning the number of sides it has. Hexa being 6, hepta or septagon being 7. 7, of course, has 2. Octagon being 8. Nonagon being 9. Decagon being 10. Undecagon being 11, or hendecagon, also meaning 11. Then you have dodecagon being 12. And as you can see, it gets progressively worse in the naming scheme, which is why a lot of times you'll see n-gon. So you'll see a number with the gon dash gon. So you'll see like a 14-gon or 40-gon. That way you don't have to memorize all of the names for all of the possible numbers. So, but do keep in mind at least the first 10, because those are fairly common, so those will typically be shown as octagon, nonagon, decagon, as opposed to like 10-gon. So make sure you at least understand some of those. But like I said, once you get past 10, a lot of times you'll see it like this, where it's just the number gone. It makes it a bit easier for everybody.